My name is Matheus. I have a background in economics, and I worked most of my life in credit. At the beginning of my career, I was working mostly as a data engineer, like trying to get the infrastructure of one department of the bank up and running. Then, because the bank just grew so much at the time, I was kind of forced into a manager role. I didn't like it very much, so I moved back into an individual contributor role where I was focusing on credit and specifically on how to use causal inference model to optimize credit decision. And I've been working with that for the past, I think, 5 or 6 years. During the process, I wrote some books, an open source book, a book published by O'Reilly, both focused on causal inference. I had a kid. I have a second kid coming March next year, and I'm now in the process of actually retiring to become a full-time dad and maybe work on some stuff on the side. So my goal here is to talk mostly about how do we think about causal inference in the banking industry, or at least how I see it, and some of the main challenges that come with it, okay? So I'm going to share my screen now. Just give me a second. Cool. Okay. So let's talk about this. Before we jump into the credit, into the causal inference side, I just wanted to give a brief introduction to the credit business. That way I feel it's more relatable, and it might be easier for you if you want to apply this stuff to something that is not credit. It might be easy for you to do so if you understand a little bit about the business of credit, which is not unlike any business. It's a very traditional business. You'll see that this is translatable to any sort of stuff that you will find around there. So here it is, like credit card business 101. I'm going to focus mostly on credit card. This extends to personal loan and other stuff. But to keep it simple, let's focus on credit card. So what we need to think about in a business is that a business has revenues and it has costs. We need to understand where they come from. So let's look at the cost side first. We need to ask ourselves, how does a bank loses money? Well, there's a bunch of ways, but the biggest way is that at the end of each month, so essentially we give money to people on a credit card, and at the end of each month, a customer has to make a decision. Does it pay us back the money that it owes, or it doesn't pay us back? If somehow the customer decides, nah, I'm not going to pay you, then that's how the bank loses money. That's the vast majority of the loss component of a bank. And how do we model that mathematically? It's a little bit more complicated than this, but this is kind of like 90% of it. Essentially, it is the probability that the customer has of defaulting. So the probability that the customer has of defaulting times the amount of money that we gave to the customer. So sounds pretty simple. If we gave $1,000 and the customer has a probability of default of, let's say, 10%, then the expected loss is $100. And that's basically a line. So the more I increase the credit line for the same probability of default, the cost increases linearly. Of course, there are some assumptions here. For instance, we're assuming that credit line does not impact the probability of default. This is not entirely true, but it's not far from the truth. And we're also assuming that the customer default with everything that we gave to the customer, which is, again, not entirely true, but not super far of the truth. Just keep in mind that this is a simplification for the purpose of the presentation. But again, it's not super far from the truth. I would say that the simplification represents something like 80 to 90% of what truly is. So this is the loss part, right? Now let's take a look at the revenue part of the credit business. So here I'm going to focus on one source of revenue. There are two, actually. So there is interchange fee and there is interest. So we can charge interest on a credit card, but let's focus on the interchange part here. So whenever a customer makes a purchase with the credit card, bank takes a small fraction of that purchase, which is called the interchange fee. So we take a very, very tiny percentage of every transaction that the customer makes. Say the customer wants to buy a ticket to a concert and it pays X amount of dollars. We take a tiny fraction of that X amount of dollars and we take it for ourselves. And since that's how we generate interchange revenue, basically it's going to be mostly a function of the customer's, what we call the customer spend curve. So it's basically how much the customer is going to spend times the interchange rate. Now, this function here is not something I know. I don't know how the customer is going to, how the customer spend is going to respond to credit line. But we can kind of assume that it's going to, we can assume some stuff about it. For instance, it's almost certain that this curve has this concave shape here, or that it saturates. And the reason is that at some point, the customer reaches what we call the customer becomes satisfied, meaning that if we give more and more credit limits to the customer is not going to spend more and more and more and more. So there is a point on which if we give more lines, the customer spend doesn't increase that much. So we say that this curve saturates. It's not a line. It's not a linear relationship, but more like a saturating curve. So we have these two components. We have losses and we have revenues. Let's now put them together. So how do we optimize lines, assuming we only have these two components? Basically, we make the following questions, right? So let's say we start at 0 and we want to know if it's profitable to give $1,000 on credit limit to the customer. So we look at extra cost. So let's say how costly it is, this decision from going from 0 to 1,000, and we say, about that's the cost. This is the cost of going from 0 to 1,000. And then we look at revenue. So what's the extra revenues of going from 0 to 1,000? And that's a big revenue, right? And importantly, this extra revenue is much larger than this extra cost, meaning that if I make this decision from going to 0 to 1,000, I'm going to make much more money than I'm going to lose money. So the extra spend is bigger than the extra loss. So it makes all the sense to make this decision of going from 0 to 1,000. And I can make this question again, like, should I go from 1,000 to 2,000? Okay, let's look at extra cost. Extra cost is still relatively tiny, and extra revenue is bigger than extra cost. So it makes sense to make this move. So I'm going to go from 1,000 to 2,000. At some point, because the revenue curve is concave, what's going to happen is that at some point, the extra revenue is going to become smaller than the extra cost. So for instance, here, if I want to go from 2,000 to 3,000, I'm going to see that my extra revenue is kind of not that big anymore, and it's smaller than my extra cost. So if I go from 2,000 to 3,000, I'm actually going to be losing money if I make this decision. And so I stop there. I don't make this move, which basically means that my optimal line sits somewhere around here. For those familiar with economics or microeconomy or Econ 101, if you ever took some course that included those subjects, this is the good old marginal revenues should be equal to marginal cost. So that's why I mean that the credit business is nothing super fancy, it's nothing super weird. It's like basic microeconomic theory. We can apply it here. It basically says, let's equate extra spend to extra loss, or marginal revenues to marginal losses. This is a problem of the firm. This is the technical term we call in microeconomy, but we're just applying to the credit business. Okay, so this is how a very simplified, of course, a very simplified way of seeing the credit business, but this is how the credit business operates. Now we need, of course, to estimate both of those parts. We need to understand this is how we do optimization, but now we need to estimate the revenues and we have to estimate the loss function. So we're going to do those things now and see how causal inference plays a role in it. This is just opening up those functions like from what we saw previously. So marginal revenues equals marginal cost. And specifically for this problem here that was simplified, marginal revenues is given by, marginal cost is given by this function here, and marginal revenues is given by this function here. Okay, so let's estimate each one of them in turn. I'm going to start with marginal loss first, because I think it's going to give us a nice introduction and some contrast to what we're seeing in the marginal revenue part. So for the marginal loss part, this is what we call underwriting. So if we take the derivative of the loss function, so if we differentiate this part here with respect to credit line, the derivative is very simple. It's just risk, right? So the slope of the red curve is basically the probability of default. So if I can estimate this part, it's problem solved. I found the derivative of the loss function. And this is what we call underwriting, and it's very traditional in banking industry because basically every bank does that. It tries to predict what is the likelihood that a customer will default on a loan or on a credit card. And it's that simple and it's that easy in the sense that risk is something I can observe. Like I know from my past customer, if I gave money previously, I can see if a customer defaulted or not. This is a very simple and a very traditional machine learning problem, or a very simple estimation problem. Basically, I could just pick whatever machine learning model I like best, and I can just estimate the probability of default given a bunch of covariate X, a bunch of features, let's say, to my machine learning model, call it a day, job done. So it's that simple. Oh, it's not that simple. There are like details there you have to take into consideration, but for the purpose of, since the goal here is to focus on causal inference, here I don't really need to take into account a lot of the causal inference aspects of the problem, because the derivative here is super simple. Like there's no treatment here, like the derivative is just probability of default. So I don't need to take special care into any aspects of causal inference. It's basically just a traditional predictive machine learning problem. Okay. So this traditional predictive machine learning problem solves half of my optimization equation, solves half the problem, the functions that I need to estimate. It solves the loss function. Now let's contrast this with estimating the marginal revenue. So estimating the revenue part. Now this is a little bit more complicated because, so this is the revenue function, and it's interchange rates times spend, which is a function of credit line. But basically, if I want to differentiate this part with respect to credit line, I need to differentiate on something that I don't know. Like I have no idea what's the spend function of my customer. I have no idea how much a customer is going to spend if I give a credit line or not. So this is basically something unlike the credit underwriting problem, which I cannot observe the thing that I will want. I cannot observe the derivative of my revenues function, unlike in the case of underwriting. So this is very much a causal inference problem because I'm going to be interested in the slope of the spend function, with respect to credit line. So to make this a little bit more concrete, what I want to be able to do is I want to find ways to separate my customers into customers that are very sensitive to credit lines, like those ones here on the right, from customers that are not so sensitive to credit line increases, like the ones in the left here. So I'm basically trying to segment my customers into more sensitive to credit line or less sensitive to credit line. And notice that this is a very different problem than trying to simply predict how much my customer is going to spend. For instance, if I take the spend curve here and I move up and down, my optimal point doesn't change at all. Like the optimal point is just a function of the steepness of this curve. It's not a function of how high or how low this curve is. So I'm not entirely interested in predicting how much a customer is going to spend. I'm only interested in understanding how the spend changes as I change credit line. And this is a causal inference problem. This is a problem of estimating treatment effects, and specifically of estimating the effect of credit line on spend. Now, there are two issues that arises when you try to estimate the effect of credit line on spend. The first is a problem that arises in any causal inference problem, or in most causal inference problem, which is bias. So if we look at historical data from the bank and we try to estimate this relationship in historical data, what will very likely happen is that we will underestimate this relationship. And the reason for that is the bank tends to give more credit lines to customers that are less risky. And for the same credit line, customers that are less risky tend to spend less. So let me rephrase that. The bank gives more money to people that spend less. So if I look at my data, like it's going to look something like this, while my true relationship is probably much steeper than if I simply plot what is the average spend given the average credit line. So if I naively try to estimate the relationship between credit line and credit spend, I'm going to underestimate the derivative of my spend function. So this is problem number one. Problem number two is that I'm not only interested in estimating the correct relationship between credit line and spend, I'm also very much interested in treatment effect heterogeneity, meaning that I want to find people that are very sensitive to credit line, and I want to separate those people that are very sensitive from the people that are not so sensitive to credit line. In other words, I want to find people that respond super well to the treatment and people that don't respond so well to the treatment. I want to segment my customers into more sensitive and less sensitive to my treatment at hand, which is the credit line. So ideally, I would come up with a model that basically does this split for me. Like I throw a bunch of features, the model basically says, hey, this customer is super sensitive to credit line increase, you should give more credit line to him. This customer is not so sensitive to credit line increase, so don't give a lot of credit lines to him. And the goal here is basically to give more different limits as possible. So the more diverse my credit limit portfolio is, the better, of course, if it's accurate. But basically the goal is I want to segment in these two dimensions. So there is the loss dimension, right? So the loss dimension essentially says if a customer is more risky, or if the steepness of the loss function is super high, then I want to give less money to this customer, which is the bottom row here. Oh, sorry, the top row here. If my loss function is not so steep, so it has a very small, it's not at all steep, or the risk is very low, then I want to give more money to the customer. But given the same risk, I also want to segment in another dimension, which is the steepness of the revenue function, or the steepness of the spend function. So for the same risk, let's say for the same steepness of my loss function, a customer that is super sensitive to credit lines increase, like the blue one here, the blue segment here, should receive more credit line than a customer which is not so sensitive to line increase, right? So I want to segment into those two different axes. I want to segment into credit risk, which is the derivative of the loss function, and I want to segment in spend sensitivity to line, which is the revenue part of my equation. So this is my end goal here. I think it's important to keep all of this in mind, because this should guide every modeling decision that we make and every modeling evaluation that we make afterwards. So this is the goal here. So how can we come up with a model that does precisely this thing that we want to do? I'm not going to go into a lot of the nuances here. I'm going to give a very simple example because I want to focus on something else, which is model evaluation, meaning how do I know if I have a good model or not, because I think that's the hard part. But to do that, let me just give a simple example on how we might go about building a model that can say, hey, this customer is not so sensitive and this customer is more sensitive to line increases. So to make it more concrete, let's forget the concaveness of the function. Let's say that we have a very simple relationship between customer spend and line. And let's assume that from now on, I'm having line which is randomly assigned. So I'll not deal with the bias problem here. So I'm assuming that credit line is randomly assigned, which will allow me to only focus on the treatment effect heterogeneity problem. So no problem with bias here, no problem with bias whatsoever, and the relationship is linear, right? So let's say that this is how the data is generated, and I have two sets of feature, okay? So I have features X1, which is going to influence the level of the spend. So basically how much a customer spends, if it spends a lot or if it doesn't spend that much. So this is feature X1. And I have features 2, which is going to dictate how steep the spend curve is going to be, right? So X1 dictates the level of the spend curve, and X2 dictates the steepness of the spend curve, right? So for the purpose of causal inference, of course, we're much more interested in X2 than X1. We really don't care about the level of the spend curve. We only care about the steepness of the spend curve. So we want a model that basically leverages X2 here. So let's build this two model and see if we can compare them. And here I'm going to build a very simple model, which is basically like pick your favorite machine learning algorithm. I'm using like GBM regression because it allows me to not have to worry about missing anything else. And I'm fitting a model to predict spend, giving my set of features plus my treatment, which is credit line. And I'm going to have two models here. MY basically uses the feature that impact spend level, and MT uses only the feature that impact spend steepness. So we should expect that model T is very good from a causal inference perspective, and model Y not so much from a causal inference perspective. Okay, but this model here, they're built to predict spend. As I said before, we don't really care about spend. We only care about spend steepness or sensitivity. How can we go about obtaining that from a model that was built to predict spend? And that's basically very simple. What we can do is that let's take a model and let's make predictions at 2 points of credit lines. So I'm going to take a model and I'm going to plug line there. Let's say I'm going to make the prediction pretending that my line is 1000, then I'm going to pretend my line is 2000. So I subtract one from the other and I divide by the delta limit. So if I do this calculation here, I basically get the delta spend. So I'm basically predicting spend at 2 points in lines. So I set line to a number, I set line to another number, and I subtract one from another, and then I divide by the difference in lines here, which will give me the delta spend. So this is how I can go from a model that predicts spend to a model that predicts marginal spend or delta spend, which is the quantity that I'm interested in. Okay, so now I have two models that produce this quantity, and I want to evaluate how good those models are in producing such quantities. And this is I think, the most challenging part, and this is the interesting part of what we're going to focus here. Cool. So model evaluation. So how do we evaluate a model that predicts delta spend? There are some methods. I like this one very much. So basically, let's say that we produce a delta spend from our two models like we showed previously. And what we're going to do now is that we can do, first of all, a visual check, right? So let's say that we build quantiles using the predictions of model T, and we make quantiles using the predictions of model Y. And then we plot the relationship between spend and line given those segments of the models. What already we can see just by a visual check is that The Model T is much better at segmenting customer on the steepness of the spend curve, right? So a customer that has a very high prediction according to Model T has a curve which is very steep, and a model that has a very low prediction according to Model T doesn't have much of a steepness at all. So this is already a very good sign, right? But visual checks are not enough for model selection. Ideally, we would come up with a single number that says this model is better than that other model. So what we're going to do is that we are going to have to define an actual quote unquote quantity for delta spend. It's not actual because I cannot observe for any individual customer, but I can define this for a group of customers. So let's say that I have a group of customers. Basically, the actual marginal spend is the slope of the line between spend and credit line. On the binary case, if I only have two levels of line, this would be a lot easier. It's just what is the outcome at the control, the outcome at the treatment minus the outcome of the control. But when I have a continuous treatment case, as in the case of credit line, I have to define it as the slope of the regression line. Okay, now that we have this way to define actuals, what we're going to do is for every model that we have, so let's say for model T first, let's sort the customers according to the model T prediction. So you can see here, basically I have the customer which has very low predicted sensitivity at the top and the customers that have very high predictive sensitivity at the bottom. And what I'm going to do is that I'm going to compute my actual delta spend or the slope of my regression line of my top 1% customers. So I'm going to compute the regression line if I only take the top 1% of my customers according to the model. So if I take the top 1% more sensitive customers according to this model, what is going to be the actual slope of the regression line? And then I do this for the top 2% and then the top 3% in a cumulative manner, right? At the end, what I'm going to have is I'm going to have the top 100%, basically everyone, and this is going to give me the average treatment effect or the average slope of the regression line of the relationship between spend and line. So ideally, what I'm looking for is a model that starts with a very high slope and gradually decreases until the average treatment effect. So this is a good model. This is a model that can segment customer between more sensitive and less sensitive. In contrast, if we have a model that is not so good, for instance, like our MY model, what we can see is that it basically doesn't sort the steepness of the regression line. The regression line is basically the same regardless of the segmentation that I choose. So basically the model is just wiggling around the average treatment effect. So very nice. I have something that I can say, okay, the higher this curve is, the better. And I could just take the area between this curve here and the average treatment effect and say that this is my area under the curve, and this would be my way to evaluate my model. The model that has the higher area under the curve is better. There's one tiny problem with this metric that I really don't like, is that the majority of this area comes from the top 1% of the customer, meaning the majority of the area comes from a very small sample size. So I really don't like this because it gives a lot of variance to this metric, because I'm assigning high importance to a very small sample size. So what we can do is just normalize the metric. So basically I take the effect of the 1% and I multiply by 1%. This will give me a curve that essentially starts at 0, climb up, and then converges to the average treatment effect for a good model. So I can use the area under this curve and say that this is my metric of causal evaluation for my model. So it seems that, okay, this is fine. I can build a model for causal inference. I can use a metric pretty much like an AUC, and I can just throw whatever machine learning model, optimize it, and whatever model gives me the highest metric according to this model evaluation procedure is the best model for segmenting between customers that are more sensitive and less sensitive to spend, and this solves the issue. So it seems that everything's okay, right? But now we need to go back to reality and remember that the relationship between spend and line is not actually a line like we assumed previously. It's more of like a curve. So it has a curvature to it, meaning that depending on the treatment levels, the treatment effect is going to be more or less sensitive. For instance, if we are at the beginning of the curve, the curve is a lot steeper than if we are at the end of the curve, which is much less steep. And this is going to cause a hell lot of problems later on. So the first problem that we have is that we can no longer define the predicted delta span as the difference in predictions at 2 points on the line curve, because now it's not super clear which points should we pick, right? If we pick 2 points around this region, we're going to have a much lower predicted treatment effect. If we pick 2 points on this region here on the bottom region, we're going to have a much higher treatment effect. So the definition of prediction is not so trivial anymore because we cannot pick 2 points and call it a day. The decision of which points to pick is going to be very impactful. One way to deal with this is that instead of picking 2 points, let's pick a bunch of points, right? So I'm going to make prediction for spend at multiple points in my curve. So let's say I pick 10 points and I make predictions for all those points, which is what you're seeing here. I have the same customer, this customer here. I keep everything the same and I pretend the customer has $50 in line, 1,000, 2,000, 3,000. So I pretend the customer has all those different credit lines, and then I see what my model predicts, which essentially will generate a plot somewhat like this. So this is not the actual spend. This is the predicted spend for a single customer, and I can summarize the relationship implied by my model by fitting a regression line through the predictions. So I take the predictions and I fit a regression line, which is, you can do this very efficiently. It's just the covariance between spend prediction and line divided by the variance of line. And I can extract the slope coefficient of this relationship here. So basically, I'm fitting a regression through the predictions of my model for every single customer. And I can use that as my delta spend prediction. Now that I have a well-defined delta spend prediction, I can plot my Gini curve, my metric, just as before and call it a day, right? So I have a way to predict delta spend. I can rank customers by that prediction, and I can see if I manage to come up with a curve that has the shape that I want, meaning that it starts at 0, slowly climb up, and then converges to the average treatment effect. Seems fine, right? Well, not really, because as it turns out, there's a very simple rank ordering schema that I can come up that is very competitive with my machine learning model and that I don't really like. And let's go into that. Essentially, if I segment my customer by the treatment they receive, by the treatment where they are in the treatment curve, this is going to generate a very, very competitive Gini curve. So basically, this is what's happening here. If I take the customer that have very small treatment, very low limit, because of the curvature of the curve, I'm going to have a very high derivative. If I then take customer that have very high treatment, very high credit lines, they're going to have a very small derivatives, hence a very small treatment effect. So basically what I'm saying here is that if I use this quote-unquote model that just says what is the credit limit that I'm going to give, this by itself is a good rank ordering schema. And I don't really like this because it basically says that I should just give more lines to whoever have small lines. So the smaller the line a customer have, the higher the derivative, hence I should give more line to this customer. And this is kind of trivial. It's not like, it doesn't tell me that a customer is more sensitive or less sensitive. It basically says that this customer has small line and this customer has high line. I cannot use this to segment my sensitivity to line. So what are the solutions for that. I confess it's kind of an open question still, but we can come up with some ideas to mitigate this problem. And I think it's a very interesting area of research. So back to first principles, what I really want with my model is that basically I want to produce a model that segments a lot, that produce segments where the top segment is very sensitive to credit line and the bottom segment is not so sensitive to credit line. So basically something like this, like in this picture, model A is clearly visually better than model B. So how can I come up with that? So I want this, and not only that, I want, basically I have a relationship between line and span, which is a curve. I want to summarize this entire relationship between line and span in a curve. And ideally, I want to summarize it in a way that doesn't depend on what treatment I give, because I don't know what treatment I'm going to give in the future. So I want a relationship, a number that summarizes how sensitive a customer is to credit line and that it doesn't depend on the credit line that I give to the customer. So we tried that with slope of the regression line, and that didn't work. But what if we use a nonlinear relationship, right? So what if we use the slope of a regression line, but now we apply a nonlinear transformation to credit line? For instance, in this case, we apply the square root transformation. If we do so here I'm just taking credit line and applying the square root transformation. What we see is that we take what was a nonlinear relationship and I'm transforming it in a linear relationship. And that eliminates all the problem I'm having, because now my derivative, now my slope is the same regardless of the credit line that I give. So regardless of where I am on the x-axis, the relationship is always the same. The derivative is always the same because the relationship is linear. So this effectively removes all the issues that I had before. And now I can plot my Gini curve. And if I plot the trivial rank ordering, meaning if I plot, if I use the amount of line that I gave in the past as a way to rank order customers, we can see that it no longer has a competitive curve and that it no longer segments customers on how sensitive they are. So the trick here is to somehow come up with a way to linearize what was a nonlinear relationship. And this basically solves the problems that we were having before. Some caveats here is that this is not always possible because not all relationships can be summarized into a single point, into a single parameter. Like here, we could summarize the entire relationship between line and span as the slope of the regression line, where we apply the square root transformation for line. But let's say that we have a parabola like this. So if we have something like this, there's basically no way I can summarize this into a single data point, right? So this technique does not apply all the time. I have, for this to work, I need a way to summarize the relationship into a single data point. So this is caveat number one. Caveat number two is that once we talk about model evaluation for causal inference metric, we tend to disregard traditional predictive metrics because we say, hey, traditional predictive metrics are for prediction problems. We're solving a causal inference problem. And that's true for a lot of cases, but at least in credit, I think predictive metrics like R-squared or mean squared error can still be useful. And I'm going to be very careful when saying this. I'm going to explain why I mean this, is that because I understand that they're not perfect. So why are not predictive metrics not perfect for causal inference? Is that, let's say that you have a function that you care about, so you're trying to understand the relationship between line and span. And the function of span can be essentially modeled like this. So span is a function of line and a bunch of features x. I can decompose this function as a function f, which is the relationship between line and span. And this relationship can be modified by covariance x. And a part that just depends on the variable axis. So basically, for causal inference purpose, we only care about the f part. We don't want the G part here. The part that doesn't depend on line, we don't care about. But predictive metrics like R-squared or mean squared error, they're going to capture the G part, right? They capture everything. And basically, which means is that they are going to be polluted by this G part, which you don't really want, right? You want a metric that just captures the F part and removes the G part from the equation, and that does not happen if you use traditional predictive metrics. So that's the issue with traditional predictive metrics. However, at least in credit, the F part is much, much, much more important than the G part, meaning that credit line is a very important predictor of spend. Or in other words, that in credit, the treatment that we have is super strong. If we change the limit the customer has, the amount of spend that the customer has also changes a lot. So the treatment is very strong. Meaning that if that's the case, then G here is much more, F here is much more significant than G, which means that probably if you use predictive metric and you have a model that has a much higher R squared than a model that has a much lower R squared, this model is probably going to be also better for causal inference purpose. Of course, but if you have models that are very close to each other, then you have to be much more suspicious. Also notice that this is only for credit. If you work in other business areas where you have a very weak treatments, for instance, let's say we were trying to use emails, marketing emails to increase customer spending. Emails are very weak. Like if we send an email, it's very unlikely that the customer is going to spend more just because we send an email. So if a treatment is very weak, then what happens is that the G part dominates, and then a predictive metric is not going to be good. But if we have a strong treatment like we have in the credit problem, then I think traditional predictive metrics can be a very good proxy for how well a model is in terms of causal inferences. So this is caveat number 2, which I think is just, let's not disregard predictive metrics when we have a strong treatment. So that's what I had for today. Again, the goal was to see how we can focus on evaluation metrics. I really like this topic because for me, if we can evaluate the model correctly, basically doesn't matter how you come up with the model as long as you know it's right. I really don't care how you come up with the model, so long as I can know it's right or wrong. And that's why I'm really passionate about this part of how do we evaluate models when we have a continuous treatment and when we have this non-linearity stuff, which is almost always. So thanks everyone for the attention, and I hope you can take something out of this. Cool, so that was it. If you have any questions, please feel free to reach me out on LinkedIn. I'm always interested about talking about those stuff. You can also send me an email, Matheus Facure on LinkedIn. There you can get my email. Also, I wrote a book with a bunch of stuff about causal inference in the industry. You can, of course, purchase this. This is very much focused towards industry, and it's, of course, a paid book. If you're a little bit short on the money, there is also an open source book. It's a little bit more tailored to the academia part, but you still can get a lot of which is causal inference for the brave and true. Just search Matheus Facure on GitHub. You'll probably find it, and you can get all the content about causal inference, how we apply this to business context there. And again, any question, please feel free to reach out.